Good morning, dear children. Let us continue the lesson gravitation. Okay, last class we have discussed about universal law of gravitation, where we have found out the force between two objects. Okay, that is F equal to G m1 m2 divided by d square. And today's class we are going to discuss about free fall. Okay, about free fall. And the meaning of free fall, that thing can be understood by considering an example. Take a stone and throw it upwards. It reaches a certain height and after that it falls towards earth. Listen to it. And we have learned that earth attracts all objects towards its center. I think already we learned. Earth attracts all objects towards its center. Actually this is due to the gravitational force. That is, with the gravitational force, earth attracts all objects towards it. Okay. And here, whenever objects fall towards earth, under this force alone, we may say that objects are in free fall. Okay, and object is said to be a freely falling object. A freely falling object. Freely falling object. Okay, whenever the objects move under the influence of Earth's gravitational force, we can say that object is in free fall. Okay, its motion is actually free fall and the object is said to be a freely falling object. Listen to it. What do you mean by free fall? Whenever an object moves under the influence of Earth's gravitational force alone, we can say that object is in free fall. And the object is said to be a freely falling object. All of you got it? Whenever objects fall towards earth under the influence of the gravitational force alone, then we may say that object is in free fall. Okay, and such an object is called a freely falling object. Actually, its motion is said to be free fall and the object is called a freely falling object. Okay, do you think is there any change in velocity? Let's see. When an object falls towards earth, its direction does not change. Its direction of motion remains the same. Whenever an object moves towards earth, its direction of motion remains the same. But due to earth gravitational force, the magnitude of velocity changes. Okay, due to the earth gravitational force, the magnitude of velocity changes. Whenever there is a change in velocity, it causes an acceleration. Whenever there is a change in velocity is involved, it causes an acceleration. Okay, and here the change in velocity is due to earth gravitational force, or this acceleration is produced by the earth gravitational force. Okay, and this acceleration is called acceleration due to gravity. Acceleration due to gravity. Here actually the acceleration is produced due to the earth gravitational force. That is why this acceleration is named as acceleration due to gravity. Okay, that is whenever an object moves towards earth, there is a change of velocity due to the earth gravitational force, and this change in velocity causes an acceleration. Actually, here the acceleration is produced due to the Earth's gravitational force. That is why the acceleration produced in this case is called what? Acceleration due to gravity. Okay, so we can define this acceleration due to gravity as whenever an object falls towards earth, an acceleration is produced on that object. Here this acceleration is due to earth gravitational force. So this is called the acceleration due to gravity. Listen it. The acceleration produced on a freely falling object due to earth gravitational force. Okay, the acceleration produced on a freely falling object due to Earth's gravitational force is called acceleration due to gravity. What is acceleration due to gravity? The acceleration produced on a freely falling object due to Earth's gravitational force. That is called the acceleration due to gravity. Actually, it is denoted by the letter small z. It is denoted by the letter small z. Okay, and here the unit of acceleration is same as that of ordinary acceleration A. So, you know what is its unit? The SI unit is actually meter per second square or meter second raised to minus 2. This is the unit of what acceleration due to gravity. Okay, actually it is same as that of acceleration A. Here the acceleration is produced due to Earth gravitational force. That is why we call that acceleration as what? Acceleration due to gravity. So its unit is same as that of acceleration. Okay, that is meter per second square or meter second raised to minus 2. Okay, here the acceleration is denoted as small g. You know what is capital G? Don't get confused with the capital Z and small z. Capital G is already we learned. What is capital G actually? Universal gravitation constant. Capital G is actually universal gravitation constant. Okay, you know the value of capital G. What is 6.673 into 10 power minus 11 Newton meter square per kilogram square. That is the value of capital G. That is actually universal gravitation constant. But here the acceleration due to gravity is represented as small g. Okay. And its unit is meter per second square or meter second raised to minus 2. Then what is acceleration due to gravity? The acceleration produced on a freely falling object due to Earth's gravitational force is called acceleration due to gravity. Okay. Next we are going to derive an expression for acceleration due to gravity, that is small g. An expression for acceleration due to gravity or small g. You know, by Newton's second law, Newton's second law, force is the product of mass and acceleration. By Newton's second law, force is the product of mass and acceleration. That is F equal to, we can written as m into A, mass into acceleration, m into acceleration. Okay, mass into acceleration, that is F equal to m into A. Here we are considering, in order to find an expression for acceleration due to gravity, here we are considering Earth and the object. So here the force is between Earth and the object. Okay, here the object moves towards Earth due to Earth gravitational force. Okay, so here the acceleration produced is not A. Instead of A, we have to write a small g. Here the acceleration is actually due to Earth gravitational force. So that acceleration is called the acceleration due to gravity small g. So here in order to write the force between Earth and that object, we have to write mass into, instead of A, we have to write the acceleration due to gravity small g. So F equal to m into g. That is equation number 1. Okay, the force between the object and the Earth, that is F equal to m into g. That is, this equation is written on the basis of Newton's second law. But you know, by using Newton's law of gravitation or universal law of gravitation, also we can write an expression for force between this object and the Earth. Okay. You know, what is the mathematical expression for Newton's law of gravitation actually? That is F equal to, you know, G m1 m2 divided by d square. That is the force between two objects using Newton's law of gravitation. In the same way, we can write an expression for force between the object and the Earth. Here the object mass is taken as small m and the mass of Earth is taken as capital M. So we can write the force between the Earth and the object on the basis of universal law of gravitation as F equal to G, Earth mass m, capital M, then object mass small m divided by the distance between the object and the Earth, that is d. So we can write d square. Let it equation number 2. Okay, then comparing 1 and 2, we can write mg is equal to g mm divided by d square. This m This m cancel because the same object. So we can cancel this m. So we can write g equal to gm by d square. Actually this is an expression for acceleration due to gravity. G equal to gm by d square. Next we are assuming that if the object is placed on the surface or near the surface of earth. Suppose if the object is placed near the surface or on the surface of earth, then instead of d, what is the distance between this object and the earth center? Suppose if the object is placed on the surface, actually the distance between the object and the earth center, that is equal to its radius itself, the radius of earth. In that case we can write r instead of d. So we can write gm by r square, gm divided by r square. Actually this is an expression for acceleration due to gravity. Small g is equal to gm divided by r square, where capital G is actually universal gravitation constant, then capital M, that is Earth's mass, and then r is actually Earth's radius. Actually this is an expression for acceleration due to gravity, isn't it? And here from Newton's second law we can write the expression for force as F equal to m into a. Okay, here actually we are considering the object and the earth, the force between the object and the earth. Okay, and here because here the acceleration is produced due to earth gravitational force. So instead of a we have to write a small g, acceleration due to gravity. So F equal to mg. Let it equation number 1. You know, the force between two objects can also be found out by Newton's law of gravitation. Okay, by using that law we can find the force between the earth and the object. Okay, that is F equal to g mm divided by d square, where capital M represents the mass of earth, small m represents the mass of object. So we have two relations for force. First is F equal to mg and the second is F equal to g mm divided by d square. Then comparing 1 and 2 we can write mg is equal to g mm divided by d square. These two m's we can cancel, then g is equal to gm by d square. Suppose if the object is placed on the surface of earth, then the distance between the earth and the object is equal to its radius, that is radius of earth. So instead of d we can write r, the radius of earth, that is the expression for small g as gm by r square. Okay, the expression for acceleration due to gravity, g is equal to gm by r square, where g represents the capital G stands for universal gravitation constant, and capital M, that is earth mass, and capital R, that is the earth radius. Okay, then what is the expression for acceleration due to gravity? Small g is equal to gm divided by r square, gm divided by r square. Okay, let's see the variation of acceleration due to gravity. Okay, next we can see the variation of acceleration due to gravity. You know the expression for acceleration due to gravity as g is equal to gm by r square. Okay, g is equal to gm by r square. Here the capital G, that is universal gravitation constant, that is a constant, and Earth's mass, that is again a constant. Here only the changing factor is the Earth's radius. So G is actually proportional to 1 by r square. Okay, G proportional to 1 by r square. That is there any variation in the radius of Earth, the acceleration due to gravity also changes. Acceleration due to gravity also changes. You know, the Earth is not a perfect sphere. Okay, actually it is flattened at the poles and bulged out at the equator. Okay, Earth is not a perfect sphere. Actually it is flattened at the poles and bulged out at the equator. So we can say the polar radius RP, that is less than the equatorial radius. You know, the polar radius is less than the equatorial radius. That is, as we move from poles to equator, the radius going on increases. The radius going on increases. Okay, the polar radius is less than the equatorial radius. Okay, then come to this expression G proportional to R square. Then what happens when R increases? What happens to G? You know, when a denominator increases, what happens to this G? That will decrease. Okay, that will decrease. Okay, as R increases, the value of G decreases. So here, the polar radius is less than the equatorial radius. Polar radius is less than the equatorial radius. That is, at the poles, the radius has a less value. So the G is greater. Okay, G is greater at the poles. The value of G is greater at the poles than at the equator. Okay, than at the equator. Since polar radius is less than equatorial radius. Since polar radius is less than equatorial radius, the value of acceleration due to gravity is greater at the poles than at the equator. Than at the equator. Listen to it. Here, the poles, actually the earth, actually it is not a perfect sphere. It is flattened at the poles and bulged at the equator. So we can say the polar radius is less than the equatorial radius. Polar radius is less than the equatorial radius. Okay, that is as, so we can say as radius increases, what happens to G? That will decrease. Or another way you can say as radius decreases, the value of G increases. Okay, since the polar radius is less than the equatorial radius, the acceleration due to gravity is greater at the poles and minimum at the equator. We can say it is greater at the poles and minimum at the equator. Also we can say the value of acceleration due to gravity is greater at the poles than at the equator. Okay, why the value of acceleration due to gravity is greater at the poles and minimum at the equator? Because the polar radius is less than the equatorial radius. Polar radius is less than the equatorial radius. So we can say the value of acceleration due to gravity is greater at the poles than at the equator. Listen to it. That is about the variation of acceleration due to gravity with the Earth's radius. Next we can find the value of small g. Next we can find the value of acceleration due to gravity. Okay, you know the expression for acceleration due to gravity, g as gm by r square. You know the value of capital G as 6.673 into 10 power minus 11 Newton meter square per kilogram square. And the mass of earth is 6 into 10 power 24 kilogram. And the radius of earth is taken as 6.4 into 10 power 6 meter. Then we can substitute all these things in the expression for acceleration due to gravity, that is gm by r square. Okay, and simplifying this, we will get the value of small g as 9.8 meter per second square. That is the value of acceleration due to gravity. It is very, very important. What is the value of small g or acceleration due to gravity? 9.8 meter per second square. Then what is the value of capital G? Universal gravitation constant 6.673 into 10 power minus 11 Newton meter square per kilogram square. Okay, don't confuse with the capital G and small g. Capital G is universal gravitation constant and it has a value 6.673 into 10 power minus 11 Newton meter square per kilogram square. And the value of small g, that is acceleration due to gravity, that is 9.8. Acceleration due to gravity is small g. Its value is 9.8 meter per second square. Actually, that is the calculation of small g. Okay, you know the expression for small g, gm by r square. In this expression, we can substitute the value of capital G, then mass of earth and radius of earth. Then after simplifying this, we will get the value of small g as 9.8 meter per second square. Next is the motion of objects under the influence of gravitational force of earth. Okay, the motion of objects, how the objects move under the influence of gravitational force. Let us consider an activity to understand whether all objects, solid or hollow, big or small, will fall from a height at the same rate. Okay, for that, take a sheet of paper and a stone. Drop them simultaneously from the first floor of a building. Okay, here whether all the objects fall simultaneously or fall at the same rate, whether it is hollow or solid, then big or small. When we drop from certain height, is it fall towards earth at the same rate? Okay, in order to understand this thing, we are considering an activity. For that, we have to take a stone and a paper, then drop them simultaneously from the first floor of a building. Listen it and observe whether both of them reach the ground simultaneously. We have to check whether both the objects, that is both the paper and stone, reach the ground simultaneously. Okay, can you guess which one will reach the ground first and which one will reach the ground later? We'll observe that, or we can see that the paper that reaches the ground little later than stone. Okay, the paper that reaches the ground little later time than the stone. Okay, actually, how did this happen? Actually, this is due to the air resistance. Actually, this is due to the air resistance. Actually, the air resistance due to the friction, to the motion of falling objects. Okay, actually, this happens due to the air resistance, and air resistance due to the friction. Okay, the frictional force to the motion of falling objects. Okay, that is the resistance offered by air to the paper is more than the resistance offered by air to the stone. Listen to it. The resistance offered by air to the motion of paper, that is more than the air resistance or the resistance offered by air to the motion of stone. That is why air reaches first, and after a little time later the paper will reach the ground. Okay, but if we do the same experiment in a glass jar, if we do the same experiment in a glass jar from which the air has sucked out, we can observe that both the paper and the stone will will fall the same rate. Okay, if we consider a glass jar, or if we take a glass jar and from which we can suck out the air, or we can remove the air, then conduct the same experiment using the glass jar, that time we can observe that, or we can observe both the paper and the stone falling towards earth at the same rate. Listen to it. In the first case, we drop from the top of a building, okay, the paper and the stone. That time air resistance is there. Okay, due to air resistance, actually the stone reaches the ground first and the paper second. But the same experiment that we conduct it on a glass jar, actually from which the air is completely sucked out. Okay, that time we can observe that both the paper and the stone reach the ground at the same rate. Okay. Also, we know that an object experiences an acceleration during free fall. Okay, during free fall, object experiences acceleration due to Earth's gravitational force, and that acceleration is given by G is equal, we already learned, gm by r square. This is actually the acceleration due to gravity. Okay, here it is clear that actually the acceleration due to gravity, that is independent of object mass. It does not depend upon the mass of object. Actually here capital M, that stands for mass of Earth. So the value of acceleration due to gravity or the acceleration, that does not depends on the mass of object. Okay, and actually this means that all objects, whether it is hollow or solid, big or small, should fall at the same rate. Okay, will fall at the same rate. Okay, from this, actually from the equation G is equal to gm by r square, here the acceleration, that does not depends the object mass. Okay, this means that all objects, whether it is solid or hollow, big or small, will fall at the same rate. Listen to it. And also the famous scientist Galileo, actually he dropped different objects from the Leaning Tower of Pisa in Italy in order to prove the same thing. He also proved the same thing. Okay, that is here the acceleration that does not depends the mass. So we can conclude that all objects, whether it is big or small, hollow or solid, will fall towards earth at the same rate. Isn't it? Also, you know the equations of accelerated motion. What are the equations of motion? We know the three equations of motion. Okay, that is B is equal to U plus AT, then S equal to UT plus half AT square, then B square minus U square equal to 2AS. These are the equations of motion. Okay, and here we considering the equations or freely falling objects. Okay, or freely falling, or we consider the free fall or freely falling motion. In that case, instead of acceleration A, we have to consider G or replace A by G. Then we got the equations of free fall. Okay, so we can write V is equal to U plus GT. Actually, these are the equations of free fall. Okay, V is equal to U plus GT. Then instead of distance, here actually height. So H is equal to UT plus half GT square, and V square minus U square equal to 2GH. Actually, these are the equations for free fall. Okay, V is equal to U plus GT, then H is equal to UT plus half GT square, then V square minus U square equal to 2GH. Actually, here we replaced A by G and S by H. That means change only here. Actually, these are the equations of free fall. These are actually the equations of free fall. Okay. And here actually, you know, the acceleration is taken as positive if it is in the direction of velocity. That thing already we learned. The acceleration is A is positive. A is taken as positive if it is in the direction of velocity or direction of motion. And A is taken as negative if it is opposite to the direction of motion. Isn't it? Here A is considered as positive if it is in the direction of velocity, and A is taken as negative if it is opposite to the direction of velocity. Okay, these are actually the equations of free fall. V is equal to U plus GT, then H is equal to UT plus half JT square, and V square minus U square equal to 2GH. Okay, that is about actually the motion of objects under the influence of gravitational force of Earth. Okay, all of you got it? Okay, today's class we can just recall what are the things that we have learned today. Okay, first we have learned about free fall. What do you mean by free fall actually? Suppose if the motion of an object is only under the influence of Earth's gravitational force, then that motion is called free fall, and the object is said to be a freely falling object. Okay, next we learned about acceleration due to gravity. Then what is meant by acceleration due to gravity? Actually, the acceleration produced on a freely falling object due to Earth gravitational force, that is called the acceleration due to gravity. Okay, actually it is denoted by the letter small g, and then what is the unit of g small g? Actually meter per second square. Okay, then what is the equation for acceleration due to gravity? Small g is equal to gm by r square. Small g is equal to gm by r square. That is the equation for acceleration due to gravity. Okay. And next we learned the variation of acceleration due to gravity with the radius. You know, the polar radius is less than the equatorial radius. So the acceleration due to gravity is greater at the poles than at the equator. Okay, then we learned the value of acceleration due to gravity, that is g equal to 9.8 meter per second square. The value of acceleration due to gravity is 9.8 meter per second square. Okay, then next we came to motion of objects under the influence of gravitational force of Earth. here the value of acceleration due to gravity that does not depends the mass of the object. So we can conclude that all the objects, whether it is solid or hollow or big or small, fall at the same rate, that moves towards earth at the same rate. Okay, the next actually the equations of motion for freely falling or free fall, that is v equal to u plus gt, then h is equal to ut plus half gt square, then v square minus u square equal to 2gh. Okay, okay children, all of you study well. Okay, if you any doubt then ask to me. That is the end of today's class. Thank you children.